Hello, welcome to this new video on moment of inertia from field science. Enjoying ride in automobile? Thanks to moment of inertia. It helps automobile engineer in designing automobile that provides jerk-free smooth rides. Wondering how our engineer is able to build such long structures like Eiffel Tower? Thanks to moment of inertia, it helped engineer in designing structural alignment that had very high strength. Using Google Maps for getting direction to a desired location, or seeing an image of your home in Google Earth, or seeing an image of a distant planet, star or galaxy. All these images are taken from a satellite, from a telescope mounted on a satellite. Take such a sharp image at such a high resolution or zoom, satellite must remain rock. Again, thanks to moment of inertia, it helps satellite to remain rock steady such that they can take super sharp images. Wondering how these things are related to moment of inertia? Then watch this video completely so that you can understand it. We are going to cover all this topic in this video called moment of inertia. So let's begin with the topic of understanding what are the applications of moment of inertia and how to have an intuitive feeling of moment of inertia. Now, to have all of this, to have an intuitive feeling of moment of inertia, we need to know four things. First, what is moment of inertia? Second, what is origin of moment of inertia? What made physicists or scientists define such a term, moment of inertia? What kind of problem it solved? Third, how to have a feel of it. By this, I mean, I want to have a feel of the number. And how does it correlate to the scientific quantities that we already know? And finally, what are its applications? What are the applications of moment of inertia in real world, and how and where it is used? So let's start with this. Let us say that we have to find a moment of inertia for rectangular mass rotating about its axis as shown in the figure. Mathematically, moment of inertia is integration of r squared dm, right? Or in simple terms, it is also a summation of r squared dm over all the particles. Moment of inertia can also be described as summation of r squared dm over all the particles. In this formula, dm is a mass of small element which is at a distance r from the axis of rotation. This is dm, which is a mass of small element which is at a distance of ri from the axis of rotation. Now, this is just a mathematical definition of moment of inertia, right? However, this mathematical equation or mathematical definition doesn't give us insight into what is moment of inertia, right? So now we know that this is the definition of moment of inertia. I know this is a mathematical definition, but it is not sufficient to give me a feel, right? So this definition leaves us with a lot of questions like what are the origin of this formulation, why it is defined in such a way, how do I feel moment of inertia in real world, and finally the most important question, where it is used and what are the applications of moment of inertia, right? So we have a lot of questions in our mind. Let's begin the journey to discover, to find, to understand what is moment of inertia. First, we'll start with the origin and why it is defined in such a way, right? To understand this, let us go back a little. Origin of moment of inertia has strong relations with kinetic energy. We know that kinetic energy is defined as half mv square, where m is mass in kg and v is velocity in meter per second. Anyone who studied science would know that this is a formula of kinetic energy. But wait, this formula is actually applicable only to point masses. Now, how do I find kinetic energy of body with a finite dimension having a mass moving velocity v along a straight line? How do I find kinetic energy of this body having a mass and moving with the velocity along a straight line? How do I find it? And most of the bodies in the real world are not point bodies. They are actually a body with finite dimension and finite masses. Proper formula is not applicable to them. And how do I find the kinetic energy of a finite body? So let's start. We'll use this formula and try to find kinetic energy of a finite body, right? But this formula is only applicable to point mass, so we divide the body into large number of small sections of particles and name this particle as or part as 1, 2, 3, and so on. Then kinetic energy of the complete body serves the kinetic energy of each of these particles, right? So total kinetic energy of the body is equal to sum of half mi vi square of all the particles, correct? Now we know that this body is moving in a straight line, so all the particles will have the same velocity, that is v1 equal to v2 equal to vn equal to v, which is constant. From the above formula we can remove all the constants outside summation line, right? From this formula we can remove all the constant from the summation sign, and this sum is equal to a real actually mass of the body. If I add mass of each of the particles, what do I get? I get mass of each part of the body. So this is how the kinetic energy of the body is found out, that is equal to half mv square. Now let us go to the next problem. Let us come to the origin of moment of inertia and why it is defined in such a way, right? Long before there was a time when physicists or scientists wanted to find kinetic energy of a mass rotating about an axis with a constant angular velocity. Obviously, we cannot find the kinetic energy by using the above formula, that is V or kinetic energy is equal to half mv square, as in this case, velocity at each point varied according to the formula V equal to r omega. So velocity was not constant. So how do I find moment of inertia of this body? Solution is moment of inertia. Let us see how. To find kinetic energy of the rotating body about an axis, go back to the basics. And we know that kinetic energy of a particle is defined as half mv square, right? So in order to find kinetic energy of the whole body, what do? I just sum kinetic energy of all the particles of this body to find the total kinetic energy, right? We use the same formula. Kinetic energy of the whole body is equal to sum of kinetic energy of all the particles, all the elements, or all the small sections of the body, right? So kinetic energy is equal to summation of half mi vi square, where mi is the mass of the small element and vi is the velocity of the small element, right? But in this case, both mi and vi is not constant. It depends on each and every particle. So hence we cannot take it out of summation, right? Vi is not constant, we cannot take it out of summation. Vi is equal to ri omega, but we know that Vi equal to ri times omega, where ri is distance of particle mi from the axis of rotation, right? Vi equal to ri into omega, and in our problem we have assumed that omega is constant. Taking the constants out, we get this equation. As omega is constant in our problem, we get this equation. This summation of mi times ri square over all the particles, this summation is now called moment of inertia, and basically originated to define kinetic energy of a rotating body, right? When mi tends to 0, or if I take limit mi tends to 0, then this summation becomes an integral, right? This is the correct definition of moment of inertia. Now we know the origin of moment of inertia and why it is defined in such a way, and why there is a need to define such a quantity like moment of inertia. We go to the next topic. Now we come to the next topic of understanding moment of inertia. How do I feel it? Let us say I have an object whose moment of inertia is, say, 1 kg meter square. And what is the significance of this number? Let us try to decode this. We know that moment of inertia is integral r square dn of summation of mi times ri square. Now we take a point mass at a distance of 1 meter from the axis of rotation, and then the numerical value of moment of inertia is equal to, we take a point mass at a distance of 1 meter, then the numerical value of moment of inertia is equal to the mass of an object at a distance of 1 meter from the axis of rotation. Now if I have a moment of inertia, say, equal to 5 kg per meter square, then it is equivalent to having a mass of 5 kg at a distance 1 meter from the axis of rotation, right? So moment of inertia is, you can feel it like a moment of inertia. It is equal to mass is kept at a distance of 1 meter, right, from the axis of rotation. Okay, Now that is fine, but how do I feel it? Still not having a feel of higher or lower moment of inertia? Don't like let's do some practical. To feel moment of inertia and how it increases or decreases with distance or from the axis of rotation, just attach a string to a mass and try to rotate it with your hand at different radius. Right? Feel the difference. When the mass moves away from the axis of rotation, we feel more weight in your hand. Not having a stone and a string with you right now, take some mass in your palm and rotate it with your arm slowly. Then try to increase the radius and feel how energy required to rotate changes with different radius and heaviness. As radius increases, we need to put a significant amount of energy, maintain a constant speed, and we feel more exhausted, right? That's moment of inertia and how it increases with radius. Time to start with the application. Moment of inertia finds application at many places. Every motor vehicle uses a component called flywheel. And it is specially designed metallic wheel. This wheel is designed to have a higher moment of inertia. Higher the moment of inertia, higher the kinetic energy it can show for same angular velocity. Why it is used? Most of the motor vehicle running on fuel are 4-stroke engine. In first stroke, it sucks the air and fuel mixture into the engine. In second stroke, the compression takes place. In third stroke, actually the beginning of the third stroke, we just ignite this fuel, but it gets self-ignited in case of diesel engine, or in petrol engine we ignite by using a spark plug. After this comes ignition, combustion takes place, and temperature and pressure of this gas increases. In the third stroke, the expansion of this heated gas takes place, where part of the energy released from combustion is converted into mechanical energy, and in fourth stroke we expel combustion products out of the engine. Now you know that out of these 4 strokes, only the third stroke, which is an expansion stroke, gives power from the engine, right? While the other stroke actually are not giving power. In fact, some of these strokes will take power, like compression. It requires power for compression. But we get net power out of the engine because energy given by the third stroke is much higher than the energy required for the other 3 strokes. It is worth noting that IC engine, if it is directly connected to wheels of an automobile, then this fluctuation in energy, in third stroke we get energy, very huge amount of energy, while in the remaining 3 stroke we don't get energy, actually becomes relative. So when this engine is directly connected to wheels of an automobile, this fluctuation in energy output from different stroke will cause tremendous jerk angle on the vehicle. The motion on the vehicle will not be smooth. This problem is solved by using a component called flywheel. It receives energy from engine during the power stroke and supply it to the engine if required during the remaining 3 strokes. And at the same time, it also provides continuous energy for the movement of the vehicle. By this way, it dampens the fluctuation of energy that is provided from engine to drive the wheel and make the journey in automobile comfortable. This helps in reducing jerks to very low values so that we don't feel it. Right? Moment of inertia is also used a lot in sports. One such beautiful application is seen when a swimmer dives into a swimming pool while performing some acrobatic stunts. Let us play this video. Just after diving, swimmer performs some acrobatic stunts by rolling their body with very high velocity. However, in order to land perfectly and nicely into the water, they need to slow down their angular velocity. To achieve this, when they reach near the water, surface, they spread their body. You can see how they spread their body. See, they are starting to spread their body when they near the surface. Since kinetic energy or angular momentum, we can say that it has to be conserved. Spreading this body helps the diver reduce their angular velocity. This helps diver to land nicely into the water without any injury. I will play this video again. See, You can see in both the cases, when they near the surface, they just spread their body so that their angular velocity decreases, so that will be nicely into the water. This is one of the application of moment of inertia that sports person uses. Spreading that body actually, away from spreading that body actually increases the moment of inertia, and this in turn reduces the angular velocity. Right, I'll play this video again. See, spreading the body increases moment of inertia, which in turn reduces angular velocity, so that they can dive nicely into the water without any injury. Let's do some practical. Now, try to balance a steady top on its tip. This is the top. Try to balance a steady top on its tip. Only finding it difficult, it is almost impossible to make the top stand on the tip when it is stationary, right? However, this is not the case with the spinning top. This is not the case with the spinning top. Right? Without any extra effort, spinning top balances itself very nicely on its tip. See? Let us see why. When the top is spinning with the angular velocity of the axis of spin, this angular momentum is quite high compared to the couple acting on the top due to gravity, which tries to make it fall. Angular momentum of a spinning object is moment of inertia about the axis of rotation times angular velocity. However, higher the moment of inertia, higher is the angular momentum. Right? For the same angular velocity. Like conservation of angular momentum, linear momentum, there is a law which says that angular momentum also has to be conserved. So when top is spinning about an axis, at a higher angular velocity, this angular momentum is higher, and by conservation of angular momentum, the top is able to stay stable, more stable against small tops like action of gravity, which tries to make it fall. However, when angular velocity of the top reduces, there comes a time when the torque acting on it due to gravity becomes significant compared to the torque or angular momentum. Right? Again, let us see this thing. However, when the angular velocity, let us see it again. When the angular velocity of the torque reduces, there comes a time when the torque acting on it due to gravity becomes significant, and at this time this is the time when it starts falling, and ultimately it ends from the ground like this. This shows that angular momentum, which is the result of higher moment of inertia and angular velocity, helps in stabilizing the spinning top on its tip and prevents its fall on the ground. However, when this momentum lowers, the other momentum becomes, the other angular momentum or top or couple becomes significant, and the top falls on the ground. Right. Let us go to the third application. The third application of moment of inertia can be seen in satellites. A reaction wheel is a type of wheel. Actually, it is a type of flywheel used primarily in spacecraft for 3-axis altitude control. It doesn't require rocket or external application for that. They provide high pointing accuracy and seem particularly useful when spacecraft must be rotated by a very small amount. They are providing a very high pointing accuracy, and when spacecraft has to be rotated by a very small amount, such as keeping a telescope pointed at a star. A reaction wheel is sometimes operated as a momentum wheel by operating it at a constant velocity or rotation speed in order to imbue a satellite with a large amount of stored angular momentum. Doing so alters the spacecraft's rotational dynamics so that disturbance torque perpendicular to one axis, perpendicular to one of the axes of satellite, does not result directly in spacecraft angular momentum. And this kind of reaction will actually help in stabilizing satellite so that it can rock steady, like the example of top. While actually it was moving, it was rock steady, but when the angular momentum decreased, it fell down. Same thing is actually used in satellite to make it rock steady, so that it can take photos or images of Earth, stars, galaxies being rock steady, and then we can have a very sharp image. So the same example of the top is used in actually satellite to make it more stable. Finally, moment of inertia is used to design all structures. It also includes famous Eiffel Tower. To understand this, let us see another way to feel moment of inertia. Moment of inertia can also be defined as in terms of distance. Now, we know that mi is equal to mi times ri square. To have a feel of it, to just have a feel of it, suppose if I take a mass of object 1 kg, mass of an object 1 kg, then mi is equal to distance square. Or in fact, we can say that radius of that mass of 1 kg is equal to root of moment of inertia. Why did I do it like this? I want to make sure that you understand that higher the moment of inertia, higher is the distance. Right, from this we know that higher the moment of inertia, further apart is a mass distributed from the axis of rotation. This will let us do some experiment. Now this is a ruler, and I just want you to bend the ruler as shown in this figure, in the first way. Right, it is easy to bend. Now just rotate the ruler and as shown in this figure, and try to bend the ruler in this way. Finding it difficult to bend it the same amount, bending ruler in the second case is difficult. Know why? Answer to this question is also related to moment of inertia. Actually, it is related to how far the mass of a bending object is distributed from the axis of bending. Okay, this is axis of bending. If you go in this is a very important rule in strength of material, mechanics of materials, mechanics of solids. Okay, in this case, this is axis of bending. I am taking a small cross section. This is axis of bending, and this is the cross section. In this case, actually, this is axis of bending, and this is cross section. Okay, I take this cross section. This is just a cross section. Please do it yourself. Now you may be thinking why it is difficult to bend the ruler in the second case. Right, answer to this question is related to how far mass of the bending object is distributed from the axis of bending, and this property is directly proportional to moment of inertia. Bending axis for each of the cases is shown in this figure. Fiber or mass below the bending axis, this is the bending axis. This area, fiber or mass of the object below the bending axis, this mass actually, when we try to bend it, feels tension. While the mass of fiber above the bending axis, if we try to bend it in this way, this mass above the bending axis will be in compression due to external bending force. For the first case, the mass is distributed near to the bending axis. This is the first case, and mass is distributed near the bending axis. And for the second case, the mass is relatively away from the bending axis compared to the first case. Right? So moment of inertia in the first case about this axis is lower, and moment of inertia from this axis is higher, because mass is actually distributed away. Right? We have a feel of that. That is why I told you in previous slide that further away the mass from the axis of rotation, or in this case the bending axis, it is not rotating, but it's another interpretation of moment of inertia, and it tends to be higher if mass is distributed away. That was a feeling, and I want to use that feeling right now. So in this case, the moment of inertia, in second case, the moment of inertia about this bending axis is high as mass is distributed away from the axis of rotation. And by designing structure in a particular way, that is by increasing moment of inertia about the bending axis, engineers are able to design a stronger beam. This relation of moment of inertia with resistance to bending or strength of beam is used in design of each and every structure in the world. See, the cross section of the beam is designed in such a way to give a higher moment of inertia above the bending axis. And we know that mass located near the bending axis doesn't contribute much to the strength compared to the mass which is located further away. This means that putting mass near the axis near the bending axis, which contributes less in strength, we can put the same mass away from it for having a better strength. That is what is done here. Instead of putting mass here, which doesn't contribute much to the strength of beam, we take this mass out and put it further away from the bending axis to have a stronger beam with same mass, right? In this way we can save energy, we can save cost, and we can save natural resources. Even this design principle, the design of Eiffel Tower is based on this principle. In fact, one of the main structural components of the Eiffel Tower is beams, and to provide such an enormous strength to those beams so that it can stand loads of such a massive structure, use of these beams with actually a high moment of inertia becomes inevitable. And that was everything about moment of inertia. I hope now you have a feel of what is moment of inertia with the correct applications. Thanks for watching this video till the end.